Okay, so the mantle does not melt at once. So this is also a very important factor you have to consider during the discussion of the melting within the mantle. So we call it partial melting. Okay, partial melting means you produce some kind of melt out of the melting reaction, and then what happens is you are remained with a solid residue as well. Okay, so you have a solid residue here, and you have a melt escaped out from that. So original mantle that you subjected to melt now has changed its composition, right? The original mantle, if you had composition say F, but now already some portion of it has gone, escaped as a melt. So you don't get the F composition here. Instead, you get a different composition, say F1. Okay, so for this portion we call residue. Okay, we call residue, 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 right? So melt has gone out. Now we are left with the residue. So if there is possibility for the for this region within the Earth's interior to be further melted, for example, if more temperature or more heat is input, then this residue can also be further melted, right? So likewise, it can go continuously melting with different converting into different compositions. But actually, at a certain period of time, it will remain. I mean, it will rest without further melting, right? Because there is a limit for melting of the mantle as well. So each of these step might be represented with the degree of melting, a term called degree of melting. We will discuss details later, but just keep in mind, initially it can melt only a very little amount, like 1% of melting. So that means the majority of the mantle will remain unmelted, right? So that's why we call them partial melting. Only a small portion or small proportion is getting melted. And the residue at the first stage will further melt if you input heat more, another maybe 5%, 10%. Likewise, it can keep on melting, right? But normally, this melting can take place up to about 30% of 30% of degree of melting. But beyond that, it's very hard to be further melted. The main reason is most of the melt or most of the minerals that can contribute for melting has already consumed by that time, right? By 30% melting means it's almost all the minerals that can be contributed for melting will be finished. For example, when you consider about the composition of the mantle, I ask you to find out what is the composition of the mantle when you come for this lecture, right? So that's why I did not start with the composition of the mantle saying that okay, these are the minerals that you can find in the mantle, and these are the proportions, and this is how we can name different mantle rocks like that, right? So I didn't explain that until now, right? It's because I asked you to find out, but I don't know whether you had the time or you tried finding the composition. Anyway, we will learn them, but just keep as the introductory slide. You just keep in mind that the minerals that can contribute to melt means like mostly plagioclase, pyroxene, mainly clinopyroxene, Those are the two main minerals which can contribute to melting at the beginning stage of the mantle melting, right? So when melting melting continues, other minerals like orthopyroxenes and olivine, right, will start to melt. So when you get to melt olivine and orthopyroxene in a considerable amount, that means you have already reached up to around 30% of mantle melting, right? 20 to 30% of mantle melting. So that time, by that time, you know that already plagioclase or clinopyroxenes must almost all have gone melted and removed as melt and escaped from the region. So what happens is you are enriching your residue with OPX and olivine mostly, right? So even OPX might be ended up, and finally you are done with remained with olivine, right? So when you continue melting one stage by stage, you are enriching your residue with more and more olivine proportions, more and more OPX proportions, and then more and more olivine proportions, right? Because gradually you are removing CPX. You are removing CPX means automatically you are enriching the rest of the minerals. Rest of the minerals means mainly OPX and olivine. So if you remove OPX also, then at last what you are doing is you are enriching entirely olivine. So that's why most of heavily melted rocks, heavily melted mantle residues contain 90%, more than 90% of olivine. So that is what you call dunite, right? An ultramafic rock. So what is happening during this melting is your original mantle composition will be changing towards ultramafic composition, right? Anyway, the mantle is ultramafic, peridotitic composition, but out of that composition, also you are going for extreme ends during continuation of a melting process. So this type of process we are considering in details with the rest of the time. So just keep in mind that this is a very important process taking place within the mantle because this is not like migmatite formation like thing. No, not like that. Okay. So this is a very specific kind of a melting. Of course, migmatite formation in crustal rocks is also partial melting, right? But it is controlled by mainly bulk chemistry. But here, totally the heat controls the how the peridotite is being melted. Okay, so this is a very important aspect regarding the mantle melting. Did somebody want to raise something? Is there any question anyway? Do you hear me well? Do you hear me well? I need feedback.
Excuse me, sir.
Yeah.
Sir, අපිට sir කියන දේ ඇහෙනවා පැහැදිලි මදි. සමහර වචන sir පැහැදිලි මදි.
ඒ කියන්නේ මේ dragging වගේද? දැන් මං කියන එක ඇහෙනවද හොඳට? පැහැදිලිද?
ඔව්. සමහර වචන sir අපිට මේ ඇහෙන්නේ නැහැ. මැදින් නිකන් අර මේක bounce වෙනවා වගේ එකක් වෙන්නේ නැහැ.
මොකක්ද දන්නේ ඉෂුව එක?
සර් පොඩ්ඩක් කියලා බලන්නද අපි ඔෆිස් එකේ කෙනෙක්ට?
ඔව් මට ඔයාලා කියන එක නම් හොඳටම ඇහෙනවා. දැන් මං කියන එක මේ පැහැදිලි නැද්ද? මම මේ කතා කරන වචන ටික.
සර් ස්පීකර් එකේ අවුලක් තියෙනවද දන්නේ
චුට්ටක්
සර් ඒක
අහන්න
අපි චුට්ටක්
බලන්න කියන්නකෝ පොඩ්ඩක්. ඔව් හරි බලන්න කියන්නකෝ. දැන් කොහොමද මේ මං කියන ක්ලියර්ද? පිරකොන්න ඇවිල්ලා ඉන්නවද උතන්ට? Okay, we'll continue then. If you have again problem, please let me know immediately. Okay. We were considering about the continuous melting in the mantle and how the mantle composition can change. Okay, so we will consider details later on, and we will be considering the composition of the mantle first of all, right? The composition of the mantle. I will come to that later. That's what I wanted to ask you to come prepared with, and then we will talk about how the mantle can be melted. So this is also very important important matter that you have to consider, because there are several ways of melting of the mantle, and then the mechanisms of partial melting, the ways of partial melting, the possibilities we will consider, and then finally we will come to a very important subtopic, that is elemental behavior during the mantle melting. Okay, so elemental behavior means all the geochemical controls, geochemical processes that are recorded in rocks will be based on these behavioral patterns of elements. So major elements and trace elements will be will have to be considered. Okay, right. Somebody, can you take the mic and let me know whether my voice is clear now? Is it clear? Or are you facing still trouble? Sorry, I don't hear. Uh, just speak to the mic, please.
Yes, we can hear you.
Okay, you take the mic close to your side so that you can. Sometimes I ask questions, so you have to pass the mic among the students.
Okay, sir.
Okay, right. Okay, so we will continue then. So we'll just consider the general aspects as you know the rock cycle, right? So there is no place for a cycle to start anyway, but we normally take the melting, the magmatic melting point as the starting point of the rock cycle, right? So what is happening is mantle melting is taking place within the mantle, its mantle, and then magma is generated. Okay, here the magma is generated, and then this magma can percolate to shallow levels, right? Percolate to shallow level. That means because of light density, the magma is moving upwards. Right? So during these movements, it can branch out or it can just go straight away. Sometimes they bring up the magma as like huge conduits. So we call them magmatic conduits. Okay, magmatic conduits, and this magma will, while coming up, your the magma is passing different temperature zones, right? So you have a different temperature here uh, with respect to the original temperature, right? Maybe here T1, and at the zone of melting, it may be T temperature, right? So usually when you know when it comes to shallow levels, temperatures are low, right? So if around here is 1000 degrees, maybe here 900 or 800, and then 600, 700, like that, it's little by little getting reduced. So for a magma conduit, which brings up a certain amount of magma, will face these gradual temperature decreases, right? During gradual temperature decreases, what will happen is this magma will cool, right? Temperature decreasing means cooling. So during cooling, the magma will start to crystallize materials, crystallize minerals. Okay. So at the very beginning, everything is molten, right? Everything is molten, and that is brought up to shallow levels little by little. Then maybe one mineral starts to crystallize, because crystallization temperatures of different minerals are very different. Okay. So at a certain point, from this molten magma, one mineral can start to crystallize, and the rest of the melt will be passing upward, right? So now what has happened to this composition? So here at the beginning, you say the composition is C1, the magma composition, right? So now around here, what happens is one mineral has already crystallized. So then what happens to the magma? Its bulk chemistry changes, right? Because you are leaving behind one mineral and you are going up with the rest of the minerals. So the bulk chemistry is different. So geochemically, the magma up to here is different from magma going away from this crystallization zone. So here in this region, you have the crystallization, right? So we call that region as a crystallization zone. So from there onwards, the magma traveling is kind of a new magma now, right? Because you have already taken one mineral out of that original magma. So we call fractionated magma, right? This new magma is called fractionated magma. These terms are very important. You have to note down and you have to have yourself the description on them, right? So this is very important because I'm not going to read out any note for you, right? So you are now the fourth year students, you know how to handle with the lectures, okay? So anyway, so we call this the remaining melt as the residual melt or the fractionated melt, whatever you can call it, right? So the mineral crystallized is called the fractionated product, right? So fractionation means crystallization of a mineral out of a liquid, right? So one mineral, one or two minerals maybe, it depends on the temperature conditions and also not only the temperature, pressure also, TP conditions, because both are changing when it is ascending. We call this magma is ascending, right? Going upwards towards shallow levels, towards the surface. It's coming anyway, right? So likewise, at different zones, at different temperature zones, there may be different crystallization is taking place. So at this zone, there may be one crystallization, and at this zone, there may be another crystallization taking place. So likewise, this crystallization continues, and so maybe another set of minerals will be fractionated from the magma. So the residual composition of the melt or the residual composition of the magma will be different from the earlier stage, right? The initial stage, you can consider it as C, the composition of the C1, the composition of the magma. And once it first crystallizes some minerals or some materials, then it becomes C2. And then at another zone, at another shallow zone, there may be further crystallization. Then it becomes the C3, right? So likewise, there will be continuous crystallization. At a certain point, this magma will be totally crystallized, right? Sometimes this crystallization can take place in a interior region, like as a huge magma, like batholith or something like that, right? But interior, okay, interior in the earth's I mean below the surface. So we call it intrusive magma, intrusive magnetic crystallization, right? But if it goes to the surface and meet the surface, it can mostly erupt, right? It can't just smoothly come out, right, like this. No, it will be erupting, right? It will be erupting from a, like forming a volcano, right? So gradually it forms a volcano and it will finally crystallize on the surface, right? Cooling in this on the surface. So in surface, what you get is extrusive rocks or volcanic rocks. So here you have intrusive rocks, and on the surface, what you get is extrusive rocks or volcanic rocks. So as you already know, the main difference is the crystallization rate of crystallization, right? In the interior, it is still hot, right? Here it's still hot, maybe around 700 degrees Celsius or something, or even 500 or something maybe, right? So when it comes to the temperature gap between the melt and the surrounding, I mean, there is no big contrast, right? Magma maybe started at 1000 and gradually it decreased to 800, but still your surrounding maybe 600 or 700. So the temperature gap is not that much, right? Only 100 degree or 200 degrees. So then the crystallization will take time, right? Slowly it will take. So what will happen is you will have plutonic igneous rocks. That means rocks with prominent crystals you can see in larger grain sizes, right? But when it comes to the surface, the temperature gap is very much, right? Because it is around 30 degrees maybe, right? But the magma is still hot, around 500 degrees or 400 degrees. So that means temperature gap is large. So it's like you are putting iron rod, heated iron rod into water, like, right? So what happens? It quickly cools, right? Quench. We call it quenching. Quenching. Quenching, right? So like that, sudden cooling can happen. So this sudden cooling will result very fast crystallization, and actually there is no time left for the minerals to be be grown in good shapes or good sizes, right? So they will be affinitic, right? They will be very tiny. We call affinitic texture, right? Very small grain sizes because of the large temperature gap, and there is no time for slow cooling. The rapid cooling results very fine grain texture. So that's why volcanic rocks are very fine grain. So anyway, uh, final crystallization product, literally it should be equivalent to the melt that should have existed on the surface by the time of extrusion, right? Unless nothing happened during the atmospheric interaction, right? Should be equal. That means if this was C1, C2, C3, and then final composition is C4, if you think, right, at the time of eruption, the rock crystallized should also have a bulk chemistry. Remember, bulk chemistry of C4, ideally, right? But it does not happen normally because, during this explosion, or sorry, during this extrusion, what happens is a lot of plastic fragments and ash, everything will be get mixed and also sometimes get contaminated with the crustal materials like that. So then the final composition will be getting changed. So these are some other aspects that we have to consider during this advanced igneous petrology course, because the crustal contamination is another subject matter during the magma ascent. Okay, this is another section, it's a different section, but anyway, ideally it should be same composition, but normally it doesn't happen so, right? Okay, so we have intrusive igneous rocks and we have volcanic rocks or extrusive igneous rocks formed during this cooling and crystallization process within the crust. Now it's within the crust, right? Because initially it started at the mantle melting, and then it was taken up to the crust. Finally, it was taken up to the surface, right? So like this, the melting of the mantle makes magma, and this magma has variable composition. So you can't say a certain composition to exist always, but the igneous petrologist have measured their compositions throughout the time periods, as well as in so many locations in the world. and come up with some certain criteria to show that the magma produced will form this type of particular rock if it was erupted to a this type of a setting, and if erupted to I mean if crystallized in a interior, then the composition will be like that. Likewise, we can have some average or general understanding. So such generalizations are also there. That's why we have classified considering the mineral proportions of igneous rocks. That has been taken into consideration to classify the igneous rocks. If you want to classify the igneous rocks merely based on the geochemistry, the bulk chemistry, then it's again a little bit different thing, because there are so many factors to consider before you classify the rock, right? So but you don't need to go to that detail, but you can be with the normal classification that you know, and also newly you can adopt, and also you can combine your normal classification that you know with respect to the mineral abundances to the geochemical, with the geochemical classification as well. So we will consider them little by little later with time. Okay, so just keep in mind that this melting process is very important process in the mantle that produces all the magma, right? And another thing that you have to consider melting is the depth of melting. So that will be discussed later, because it has some different producing different compositions based on the melting depth as also, right? So we will come to that later. And if you have any questions up to this content up to now, can you just make me know? Do you have any questions? If anything you did not understand until now, very introductory stuff we were talking about. But it's okay, you can ask any question if you need some clarification. Okay, right. Before going to the next part, I just want to ask you a question. Now we will start answering from the first row. Can you please pass the microphone to the first row? Okay, I'm going to ask the average composition of the mantle. So if I ask what is the composition of the mantle, how do you answer? I don't need very specific technical details, but in general, as a geology student, how will you answer to another geology student, not for the general public, okay? To another geology student, how will you explain? Maybe one of your juniors you have to explain. So then how will you explain? So I want to know your opinion. Yeah, first row, please.
Ferrous composition is high.
Sorry, keep the mic closer.
Ferrous composition is high in the mantle.
Yeah, that's okay, but it's not the answer, I think. I'm asking if I ask what is the composition of the mantle. You said okay, let's discuss it. Okay, the next row, please. You can discuss row by row and give me an answer. Consider it's a group. Okay, one said ferrous composition is high. I'm asking
Main
what is the
minerals
composition
are
of the mantle? Yes.
main minerals are plagioclase, pyroxenes, and garnet. They are basically iron and magnesium rich minerals.
Okay, very technical details. I asked very general type of, I expected a very general type of answer, but it's okay. Yeah, next row, please.
Iron, magnesium silicates, and magnesium oxides are high.
Still the similar type. Okay, next. Next row.
Magnesium oxide, silicon dioxide composition is relatively high. Then there are ferrous oxides and manganese oxide.
Okay, next. Still the similar type. Yes, next row.
Magnesium oxide and silicate are mostly present in the mantle.
Almost the same answer. Another row. Is that all? Or but still I can see some.
Silicate mineral is most abundant mineral, and then iron and magnesium, and calcium and aluminum also present in the mantle.
Okay, next. Yes. No. Finish.
Finish, sir.
Are you sure? I can't see anyway. Okay, anyway. Okay. None of you give me the kind of expected answer. I mean, very generalized answer I was expecting. Okay. I expected someone will tell the composition of the mantle is lersolite composition, or at least peridotitic composition, at least peridotite composition. Do you know peridotite? Lersolite, maybe you don't know, but you could have, I think you know, you already know about peridotite, right? The mantle, if somebody is asked about the composition of the mantle, you have to say it's peridotitic. Okay, that means it's composed of the rock called peridotite. That is an ultramafic rock. Or otherwise, very simply, you could have told me it's ultramafic. That's enough. That's all. Ultramafic, right? Ultramafic means, yeah, then you can go for details. Calcium, it's iron rich or magnesium rich, like that. You can consider, right? Those are technical details. That's why I'm, anyway, I will come back to this one. Right, that's why I just ask you to come up with very general introduction about the mantle. Right, anyway, it's okay. Right, so just keep in mind, everything we have to start with the peridotic composition, right? So this mantle melting here means we are melting the peridotite, okay? We are melting the peridotite, peridotic composition. And then from the peridotite, we produce a melt right? So this melt goes up, forming different rock types. Okay, right. So basically, what is the mantle made of? If we want to know, then we have to look for periodized composition, right? And then how does this melting happens? How does this melting happens? We have to look for the mechanisms of melting. Okay, and another important thing is once you know mechanisms of melting, you know melts are produced in different ways at different settings within the mantle itself, and these melts, the produced melts, are also mafic in composition, right? They are not, I mean, always they are not ultramafic in composition, but mostly they are mafic in composition. But you start with an ultramafic composition here, the mantle, and you produce a melt out of that as mafic composition mainly, right? Mafic composition, but it can be ultramafic melts also. It's not, I'm not denying that, but mainly what you are getting is a mafic melt. And this mafic melt, during the ascent, what happens is, I said fractionation happens, right? Fractionation happens means formation of or crystallization of minerals. That means you are taking out some composition from that melt composition. This mafic melt, from that you are taking some components out, and you form, naturally it is formed some crystals, right? Some other minerals. Then what happens? The maficness of this melt, the nature of mafic composition will get changed, right? So if you crystallize so many mafic minerals out of the mafic melt, right? Mafic minerals, you know, as you said, iron and magnesium rich minerals. So if you are removing iron and magnesium from this melt, what will happen? This melt, the remaining melt or the residual melt which has to further go up will be less mafic, right? I don't say it's not mafic, but compared to the original status, it might be less mafic. So likewise, it can be less and less mafic, and finally it can come up with the very felsic composition also, right? So mafic melt can be converted into a felsic melt also. So this is what is happening during fractionation. So this is a very important process, melt fractionation. Not only melting is important, but also melt fractionation is also important, because it drastically change, it can drastically change its composition, its own composition, and ascend as a very different melt, right? So even carbonatic melts, we have the apatite deposit, right? It's also produced by melting, mantle melting, right? Mantle melting, and also contribution of crustal melting. Both these are two things that you don't need to worry much about, because there are debates over that, whether it is totally melting of the mantle only, or crustal melting only, or mixed type of melting. So that you don't need to think about, but just keep in mind that carbonatic melts also are some special kind of a melt coming from the mantle. It can be either fractionation of this type of we call fractionation of minerals, and then for the melt, what happens is differentiation, right? It's another term you should keep in mind. Differentiation means change in the chemistry of the original material, right? It can be either a solid or it can be a liquid. So differentiation can also lead to carbonatic magma production, and also carbonated magma can be produced as a result of some source characteristics as well. Source characteristics means the original melt might not be this pure periodic composition. Some other carbonate-rich composition can be there, right? Such possibilities are also there, right? Because you have to consider this mantle is always disturbed by subduction processes, right? All these processes that are taking place in a cyclic manner, right? Because mantle convection drives everything, as I said before, right? So mantle convection drives slabs move away from each other and subducts at the subduction zones, and then a lot of carbonate materials can be subducted into the mantle with the slabs, right? That can be further melted and come back as a carbonatic melt. So likewise, there are a lot of possibilities of and also variations of these melts formation. So anyway, the majority of mantle melts forms are mafic magmas. Okay, mafic magmas, and then finally they can be fractionated or differentiated into silicic magmas or felsic magmas, right? Because mafic magmas are very kind of dark because they are having iron and magnesium rich compositions. But later on, iron and magnesium can be fractionated away, leaving silica and aluminium rich in the mantle, in the melt itself, so that it becomes light in color, and also compositionally it will become granitic, right? Granitic melts means felsic melts. So likewise, there are such complex processes taking place from the initiating from the mantle. But anyway, most of the cases we have to consider the mantle as the peridotic composition, which contributes to melting in different degrees. Okay, so even though we say that okay, the mantle is periodic, but this periodic composition has also some large variations, right, with respect to availability of different phases, different minerals, right? So we will come to that a little later during our lecture series. Okay. Right. So before we move into details on this melting with consideration of the mantle melts, we will just briefly go through the dynamics, right? Earth dynamics, where this melting can take place at different environments, right? So these environments we generally call tectonomagmatic environments. Tectonomagmatic environments means the places within the crust and mantle where the magma can be generated, right? Tectono means tectonic process as a result of tectonic processes. Magmatic, as you already know, it's just the generation of magma. So this generation of magma with respect to tectonic areas or tectonic forces or tectonic divisions in the earth, we call tectonomagmatic environments, right? So as this this diagram shows, you can see clearly number one, this is mid-ocean ridge, right? You know mid-ocean ridges. Where do we have mid-ocean ridges, right? See, this is a mid-ocean ridge. So this is again you can call spreading ridge, right? These terminologies are very important, but these are very introductory. Even at your first year, you must have learned these things, and you must be able to explain them comprehensively, right? I mean, we don't need to learn at the fourth year about these terminologies again. So mid-ocean ridges, or we call them spreading ridges. Why we call them spreading ridges? Because the underlying magma is coming up, and due to this magma emplacement happening in the oceanic flow, right? Remember, this is oceanic flow. This is ocean, right? In the middle of an ocean, right? Consider this is an Atlantic Ocean, right? This whole area is Atlantic Ocean. So then the middle part in the Atlantic Ocean, you have mid-ocean ridges, right? Or spreading centers, spreading ridges. We call spreading centers also because it's always in the middle of an ocean, right? This is the normal occurrence. So in the middle of an ocean, gradually, little by little, even now, even just now itself, magma is dumped by this mantle convection, because this mantle convection is taking place like this. We call them convective cells, right? So it's exactly similar to boiling a kettle of water, right? If you put some ink into that and you start heating from the bottom, then you will realize heat transferring, right? Heat transferring with the material transfer, right? It's not just heat transfer like conduction. Conduction is just the heat transfer. You don't see any material transfer there. But convection also accompanied by material transfer. That means it's giving a passive force for the molecules there. They will be pushed with the heat. So that causes a tremendous force beneath these plates, and that will make these plates move away from each other, right? Divergence. So that's why we have mid-ocean ridges generated at divergent tectonic regimes, right? This is divergent tectonic regimes. So this is a weak zone. There you have a lot of magmatic push coming out from the mantle, because because of these convective forces, this plate moves this way and this part moves that way. So it becomes very weak zone here, right, in this region. So being weak zone, what happens is the mantle, which is immediately lying below, can push up, right? It can push. So it will be pushed, and the magma can be dumped at the bottom of the sea, right? So it's actually submarine volcanism, right? It's submarine volcanism. Why we call volcanism? Because even though it's ocean, it's the surface, okay? It's Earth's surface. So it's no longer intrusive, it's extrusive. So extrusive magmatism is taking place, but it's taking place in, under the ocean. So therefore, we consider it as under ocean volcanism. So anyway, this melting is taking, I mean, mantle melting is taking place. But remember, this melting is initiating at the very upper region of the mantle. So this is the upper region of the mantle here, right? So you have upper mantle and lower mantle, right? Like this. This is the entire mantle. So the upper part of the mantle we call upper mantle, and the remaining part we call lower mantle. Actually, this upper and lower mantle demarcation has come up with respect to this degree of melting. At the extreme upper regions, melting is very easy. I mean, it's very frequently happening. I will tell you why this happens later on with respect to maybe we can see a phase diagram, and then we will understand why that happens. Okay, so when the interior, I mean, say the mantle composition, periodic mantle, which is available here, with convection coming up, right? With these convection forces, it comes up. I said material transfer is happening, right? So when it comes up, temperature is also low, getting little by little low, and also the contrasting pressure conditions are faced by this mantle material when it comes to the upper levels. You know, this is some thousands of kilometers deep from very bottom part of the mantle to the upper levels. So then definitely you will face huge amount of pressure changes, right? So because of this pressure contrast, there will be a lot of melting happening, right? So you will understand later why this melting happens during the pressure decrease, right? Because no one is going to melt, I mean, no one is going to heat here, right? Because it's already molten magma is there. The temperature is say 1000 or 1500. no more. I mean, no one is igniting here to supply further heat to facilitate melting, but automatically melting starts here, right? It is because this gradual or not, yeah, this gradual decrease of pressure, right? So you will understand later on why decrease of pressure causes melting, right? We know increase of heating or increase of temperature can cause melting. That is obvious, right? If you want to melt something, you have to heat it. That's okay. But here nobody is heating because it's already heat is there, no extra heat. So it should remain as just the heated mantle, but instead, all of a sudden it starts to form droplets of melts here, right? So that is because of decrease of pressure. So we will consider that later, right? Anyway, so that melted material will be coming up to the more upper levels, more shallow levels, and dumped as the mid-ocean ridge. So I said before, these melting materials form mafic magma. Okay, so all the upcoming material coming, I mean dumped here are mafic. So actually, it's what you get is mafic melt crystallized there, right? That is what you call basalt, right? So you have peridotite originally, that is melted, and now mafic melt is produced. Mafic melt means basalt. So basalt is produced here, but this particular basalt is produced at a mid-ocean ridge, right? It's a special tectonic region, so tectonomagmatic environment. So therefore, we that magma or that basalt we call mid-ocean ridge basalt, right? Mid-ocean ridge basalt. So in other words, we have a very popular abbreviation for that, MORB. Okay, so what is MORB? What does it stand for? Mid-ocean ridge basalt. Okay, MOB. We call it MOB. So we call normally MOB melts for the melts or the magmatic materials produced at this tectonic situation, right? So MOB melts are formed here, and the rocks produced here are basaltic rocks. We call MOB rocks, right? Some people call MOB basalts, but actually B stands there already. So you can say mid-ocean ridge basalts, right? MOB rocks, just say MOB rocks. Okay, and number 2. What is number 2? Number 2, where is it? I can't find it exactly. It's intracontinental rifts. Okay, yeah, something like not there. Yeah, we have to take this place. Okay, here. This place where, yeah, I'm showing an arrow. So there are intracontinental. Intracontinental means inside it. Oh, sorry, not this one. This is oceanic plate still. Sorry, not that one. It's not shown clearly. Oh yeah, it's not shown. Okay, we have to take a continent because here is the continent part. Okay, so intracontinent means middle of a continent. Should be a middle of a continent, right? Somewhere here, right? Somewhere here in the middle of a continent, there can be melts formed, right? Melts form. Melting is taking place. So how this can happen? This can happen because of again some weak zone. Again, some weakening of the continent should take place. For example, if there are some extensional forces like this, right? The continent, within the continent itself, if there are some extensional forces, then what can happen? There can be some weak zone generated here. That means there can be some fractures formed or rifts. We call rift zones, right? This extension should first occur there. and start weakening this area, right? So while weakening this area, the underlying mantle here, this is the mantle, it can push or inject the mantle melt up to there, right? And also when this heated melt is coming up, the surrounding rocks will also get heated and get melted. So everything will get mixed and come up with new magma, right? So this is another tectonic area where magma can be generated. So this is the second place we call intracontinental rifts. Actually, these type of rifts can be formed soon after continental collision, right? But still, I cannot show you continental collision with this diagram because this is still not ready for that. I mean, this is still the subduction is going on. See, subduction is going on. So to continent collision, what should happen? All these continents should go like that, and subducted, I mean, right? Gradually subducted, and finally this continent should come up this way, and another continent should be here, right? The second continent. In between only you have the ocean, and this continent also subduct somewhere, and because you have subduction taking place in this type of a region. With that, you have continent coming, and this continent and the other continent which is approaching can collide each other, right? As soon as collision happened, what happens is it's like you are throwing a rubber ball to a wall. So you can throw the rubber ball to the wall, and you can see some kind of repulsion, right? So repulsion is also there after collision. So this repulsion causes this type of extensional forces, right? So this repulsion soon after the collision cause rifting. So this is what we call the intracontinental rifting. So that rifting will produce another type of magma, because that magma is very different from this mid-ocean ridge magma. Why? It's because the mantle here will come up, and also some rock melting is taking place from the continents, right? Contribution from the continents are also taking place. So therefore, its composition is different. Okay, so that is what you call the rift basalts, another type of mafic type of melt. Okay, rift basalts. And then third tectonic region is island arcs. So what are the island arcs? Island arc is this one. Okay, island arc you can consider at the subduction zone. So here, here subduction zone is here. When you subduct this slab, right, this oceanic plate, what will happen for the rocks that are available in this region around the subduction zone? Maybe I have to take a different color. I don't know whether you can see. Maybe let me see. The rocks around here. Yeah, what happens? Due to frictional heating here, you will have melting taking place, right? So that melt will come up to this region, and likewise, this is three-dimensional. Remember, this is a plate, okay? So it's three-dimensionally taking place. So like this, you can have a chain of islands formed. A chain of islands can be formed due to this type of melting. So this is again a different type of magma, because the environment is different. The material melted are different. It's not entirely the mantle melt, because there are a lot of subducting slab containing sediments and a lot of continental materials. So the composition is different. Even composition is different compared to this rifting zone also, because there are no sediments here, right? This is a accretion area. The sediments are get accumulated there. So entirely different, and a lot of water is also available there, hydrous melts. Here, not much water is there. Okay, So likewise, entirely different melt is produced. So this is called volcanic, island arc volcanism is taking place. Volcanic arcs means these ones, because these are produced as a chain of islands, chain of volcanic islands, like Japan. Japan is a very good example for island arcs. So island arc magma. So it's a very different type of magma, right? Its composition is different. So far this 1, 2, 3 indicates entirely different composition from each other. Composition in the sense, the geochemical composition I am referring to. Okay, mineralogically also have changes, but still we are now onwards taking much on the geochemical, the bulk geochemistry, bulk solid geochemistry. Okay, right. And then number 4 is continental margins. Continental margins. Here you have oceanic plates, right? Here you have oceanic plate, and it is not a continental margin. This is oceanic plate. But in continental margins, again, it's not clearly shown here. Okay, I have one place here. Here, this place, right? You have two continents, one continent here, another continent here, right? So this is one continent and this is another continent, right? So this continent is subducting beneath the other one. Actually, the two continents, when you have two continents, it's very hard for another continent to subduct beneath the other continent, because the density is almost same. Okay, density is almost same, so there will be no effective subduction, but still to some extent there can be some subduction. But there are some places where you have oceanic plate subduction, like here. This is not the subduction plate, but there can be places where subducting taking place, like in a subduction zone, normal subduction zone, like this, right? There again new kind of magma can be generated, right? But basically in continental margins we consider this type of situations, right? Like this, where you have continent collisional zones, their melting is taking place in between, right? So these will produce a huge amount of magma, huge amount of melts, but those are mainly of felsic composition, right? Not mafic composition, because the mantle contribution for that is limited, right? Because these two are continents, right? Friction and other as a result of collision, there will be a lot of melting taking place. So that continental magma will produce felsic magma mainly, but still they have the possibility, if there are a lot of lower continental crust is involved, then there can be mafic melts produced. Okay, because the continent also can be considered as two portions, upper continent and lower continent. Lower continent is lower continental crust is mainly mafic in composition, right? You have to know that, because this is a preliminary understanding about our Earth's interior. Okay, so upper continental crust is mainly granitic composition. Lower continental crust is basaltic composition. So if the melting is majorly taking place in the lower continental part, then you are getting basaltic composition. Otherwise, you will get granitic composition. So in active continental margins, both type of magmas, like mafic melts as well as felsic melts, can be produced. So active continental margins have mixed type of melts produced, right? So this is another situation, right? Okay, I should have consider the below diagram for you to understand the fifth one, back arc basins, the other region, tectonomagmatic environment where magma can be produced. is the is the back arc basins. So what is back arc basins? What are the arcs? We have already talked about arcs. Remember island arcs, right? Island arcs. Can you consider island arcs here? By the way, do you hear me well? Please let me know if do you hear me well? Because there was an interruption. Quickly, please. Whoever having the mic, please speak.
Yes, sir.
Okay. Right. So back arc basins. Back arc basin. Okay. Arc means subduction zone. Okay. Remember, it can be either oceanic arc or oceanic continental subduction, whatever. Right. Arc is subduction place, subduction zone. And here you have more clear diagram. Just a minute. Yeah. Here you have arc. Arc means the subduction zone, as I mentioned here. Okay. So this arc region, as I said before, number 3, island arc is produced here. Also the same thing. Okay, island arc. And back arc means not a little bit far away from this immediate subduction zone, right? So that means you can't see it clearly. Okay, I'll go for blue here. So immediately away from the subduction zone here, right? Somewhere here in this region, in number 5, this number 5. Okay, so this is the real arc. This is the real arc region. Actually, we call it frontal arc, the fore arc, the front region of the arc, subduction zone, right? This is the frontal arc, and this part is the back arc. Okay, just away from the front, the subduction front, because subduction is taking place like this, and this is the frontal portion, and this is the back arc region. So arc, back arc means, normally arc means frontal arc here. Back arc means away from the subduction zone towards the continent. Here you have the continent. Okay, here you have the continent. So back arc region is here. So why this back arc region produces melt? Can anybody think why this happens? Because melting, the subduction is taking place like that. So it is not just subduction. You have a connected slab, connected continent there, here, right? So this is not much moving. So it's almost stationary, but you are moving this slab, right? So this slab is moving, and at the same time, at a certain stage where the subduction almost going to end, right? It will end up with a slab break, right? Slab break means somewhere in the middle, this slab will be broken down, and part will be going down or sinking down to the mantle. So what happens as soon as this breaking happens? Again, like bouncing a ball, right? I mean, if you throw a ball to the wall, it will bounce back. So the similar thing will happen just soon after this breaking, just to respond to the isostasy. This slab tends to come up, I mean, bounce back, tries to bounce back. So when it tries to bounce back means you are like pushing from this side, along this direction. So you are pushing this direction means automatically there will be extensional forces occurring in this region. Some extensional forces will generate there. So that creates a weak zone here, and along this weak zone, there will be mantle upwelling. Upwelling means moving up the mantle melts, right? Like in the mid-ocean ridge, this mantle upwelling, we can call mantle upwelling here also. Like in the mid-ocean ridge, the magma will come up to this setting. So that magma we call back-arc basin or back-arc magma, right? The region is called back-arc basin. The magma which is originated there, we call back-arc magma. Okay, so that is the fifth setting. The magma is produced. That composition is also different because the environment here is very different from the previous four types of environments that we have discussed. Okay, right. And then number six is ocean island basalts. Ocean island basalts. Ocean island basalts means some kind of islands are produced in the middle of oceans, right? It's not the islands that produce at subduction zone. At the subduction zone, what we had was island arcs, right? Here, island arcs. But these are different because this is just in the middle of a continent, sorry, an ocean, where mid-ocean ridge is already there, but away from the mid-ocean ridge in this region here. Here, in this region here, oceanic islands are produced. But normally, these oceanic islands are produced as a result of deep magma, not shallow magma like here. So here in the mid-ocean ridge, you got shallow magma. Remember here, the situation? I said the uppermost part of the mantle is getting melted, right? The uppermost part of the mantle is getting melted there. So you get the MOB or mid-ocean ridge basalt produced. That basalt was originated at the extreme upper portion of the mantle, or otherwise the upper mantle. But here, the difference is the magma generated from very deep part, somewhere here. See, very deep part. So you know the depth here, about 2,700 kilometers below to the surface. The very much deep, right? Some thousands of kilometers down, right? It's actually the core mantle boundary, right? See here, core mantle boundary. This is the core mantle boundary because from there onwards you have the core. You have the core here, right? So this is the extreme lower part of the mantle, the lower part of the lower mantle, right? It's very, very hot. This region is very, very hot. But most of the subducting plates like here, right? Subducting slabs. I mentioned the subducting slab is broken here. Remember, this type of broken slabs move down, right? Sometimes they can go down and down, very, very deep parts into the mantle, right? And even they can reach the lower mantle region. And due to the physical difference between core and mantle, these slabs, the portions of slabs throughout millions, thousands of millions of years with the Earth's history, they get stored in this region, right, as subducting slabs, subducted materials. So such materials will get melted in this region at certain periods of time, right? We don't expect every day this melting is taking place, but normally it happens every 400 million years time, or about 200 to 400 million years time, right? So they are coeval with a supercontinent formation, right? Normally we call this a special type of magma form there, and we call this magma which has a very high temperature because of this high temperature in the very deep part of the mantle, and also very high pressure, and they can come up very fast, and hot magma, and can exert a huge amount of force below the oceanic plate there, and rupture that plate in this type of places, so that it will come up in a region like in a middle of a ocean, or even middle of a continent. That can happen, whatever, right? So such kind of magmatic flow we call magma plume, magmatic plume, right? Mantle plume, because it is starting from the bottom part of the mantle, right? So this magma is very, very different composition and also having very high temperature, and it can come up and erupt at some places in the ocean floor, or even it can hit a continent also, right? If this melting happened somewhere here, it can hit directly the continent, right? So this continent will be broken into pieces. Actually, the supercontinents, I think you can remember supercontinents like Colombia, Rodinia, Gondwana, like, right? Those are huge continents, very difficult to rift, very difficult to break down. I mean, to fracture, like not like this fracturing, right? It's very hard because they are huge supercontinents. But this type of plume flows can hit these huge supercontinents and break them into fragments. So that's how supercontinent dispersal is taking place. So that's why supercontinent cycle is coeval with plume cycle, right? Supercontinents are producing every 200 to 400 million years time, right? One continent, one supercontinent is finished, and new supercontinent will be formed, and it will be destroyed again every 200 to 400 million years time, right? So that is because of this cyclic plume activities. Okay, so one plume, the island Hawaiian Islands are product of plume some time ago, right? So this plume magma is also having very different composition. All the trace elements, rare earth elements are all behaving differently than these 5 previous tectonic situations. Okay, and you can see here a new plume is generated there, right? So another 100 or 200 million years later, it will reach this surface and produce volcanic island or ocean island basalts. So when it comes out, we call ocean island basalts because it will produce a new island here, but it's different from this volcanic arcs, because volcanic arcs are concentrated at the subduction zone, right? Here at the subduction zone, but here it's the middle of the ocean plate. But it's different from mid-ocean ridge also, because mid-ocean ridge basalt produces only mantle melts from upper part of the mantle, the shallow mantle. But here, deep mantle melting causes that magmatic production. That is number 6. And there can be other types of magmatic eruptions, such as kimberlites, carbonatites, anorthosites, flood basalts, many types of other types of basalts we can have. Actually, kimberlites means again very deep part of the mantle, and these kimberlitic magma can come up anywhere in a place, especially in it's different from plumes anyway, because they are not as deep as plume environments. They can carry diamonds, because diamonds are available in this middle regions of the Earth's mantle. And usually when this magma is coming up, it carries diamond also. That means that magma is produced at a diamond stability zone, right? To produce diamond, you need depths like 200 kilometers at least. Okay, so the middle of the mantle can produce these kimberlitic magmas, and carbonatitic magmas can be produced at several situations. Again, for example, these subducting slabs, if they contain a lot of carbonates here, for example, okay, and if in any case, if these carbonatic materials get melted due to some reason, probably it might hit with this interior magmatic zone like here. So the carbonate materials will be melted and come up here as carbonatite magma, or even it can come up from here as carbonated magma. So likewise, there can be a lot of places where carbonatite magma forms, where the source should be carbonate-rich materials, and also in subduction zones like here, carbonatite magma can be formed because of melting of high pressure rocks. Here, the high pressure rocks are there, metamorphic rock, high pressure rocks like eclogites. We call eclogites. There are a lot of calcium-rich eclogites are there. Calcium-rich minerals are there, right? Spinopyroxene is a calcium-rich, and such. There can be a lot of calcium-rich materials available. What you call eclogitic materials can melt into carbonatites. They can produce carbonatites. Okay, so they will come up as carbonatite magma. And anorthosites means anorthite is plagioclase feldspar, right? It's again calcium rich, but it's a silicate anyway, right? So that type of magma, there are various combinations of types of magmas produced at different locations in the tectonic situations. But unlike the previous 6 locations, 1 to 6, these locations, these kimberlites, carbonatites, anorthosites, and also flood basalts, they are not very regional. Okay, they are localized. They are not found everywhere in the world. Only in some places only, right? Kimberlites, for example, you can find them in African continents, right? Not everywhere. That's why Africa has a lot of diamonds. Carbonatites also not everywhere in the world, only few localities in the world. Luckily, we also have one in Sri Lanka. Anorthosites, we also had some localities, but very rare. But I don't think we can find them still. In the Seruvilla area region, right, there has been evidence, but we can't find it now. We went, many people go there, geologists, to find anorthosites there because of previous reports, but now we don't see them, right? Maybe some localized anorthosites were there. Flood basalts means some basalts make some regional distribution, especially within the continents, continental zones, and they form kind of layered type of basaltic rock units, right? So anyway, these tectonomagmatic environments are very important. Throughout the globe, you can find at least 1 or 2 of these settings, igneous settings, as products from mantle, or as a contribution from the crust and sediments as well, right? But majority is coming from the mantle. Okay, so this is a flood basalt. Normally it's almost like intracontinental, but only thing is they are spread to a large area, right? Not along with the rift zones like this, right? It's just a rift area where you have a rift type of basalts. Okay, so this is the basic type of an introduction about this tectonomagmatic environments. And about mantle melting, we have to discuss in detail, because we want to have a knowledge about different melts available, different types of melts available within the different tectonic situations in the earth, before we discuss more about melting process itself. Okay, right. So do you have some questions on this content? Do you have any questions? So any place where you did not understand? So this is lithospheric mantle. Here you can see lithospheric mantle. Okay. Lithospheric mantle means, I think you know already, the solid part of the mantle, because the mantle is majority of its nature is semi-solid, right? Like a gel, right? It can flow, right? It can flow. You know, gel can flow. I mean, deform easily, move, but it's not a liquid, and also it's not a solid. But this part, the shallowmost part of the mantle, beneath the continent or beneath the oceanic part, we call lithosphere, right? So continental lithosphere and oceanic lithosphere, right? That part. So it's a solid part we consider, right? So normally the melting is taking place when everything is coming to the very shallow region here, right? Somewhere here. Okay, so if you don't have any questions, I think we will stop here for today. I will continue next time, but you have to read about your previous notes. I mean, your third year igneous petrology, right? Because we are not going to do repetitive lectures, classification and other things, but we have to focus on very specific sections in igneous petrology, where normally the general students or normal level we are not touching it. Okay, so especially the mantle melting related things, and then geochemistry related aspects, igneous chemistry related aspects, how trace elements behave in igneous systems, like that, right? This is a very specific course. That's why it's advanced igneous petrology. So you will learn a lot of new things in this section, right? I mean, it's not very easy at once to absorb, right? Therefore, you must have previously, I mean, you must have good previous knowledge for this understanding in further lectures to come. Okay, right? Everyone should sign the attendance sheet. So please sign it and submit to the office, and your attendance is very important. It will be definitely counted. Okay, the attendance, 80% attendance must be there. And I will give you some assignments as well, and practicals will follow later. I will let you know about the practicals later on. We need specific samples also for this, which is in parallel with the course content. Okay, so I'm going to stop here now. Please submit the attendance sheet. Yeah.